The RepRap project started as a British initiative to develop a 3D printer that can print most of its own components and be a low-cost 3D printer, but it is now made up of hundreds of collaborators worldwide. RepRap uses an additive manufacturing technique called fused filament fabrication to lay down material in layers. A plastic filament or metal wire is unwound from a coil and supplies material to produce a part. The project calls it fused filament fabrication to avoid trademark issues with the fused deposition modeling term. As an open design, all of the designs produced by the project are released under a free software license, the GNU General Public License. Due to the self-replicating ability of the machine, authors envision the possibility to cheaply distribute RepRap units to people and communities, enabling them to create complex products without the need for expensive industrial infrastructure including scientific equipment. They intend for the RepRap to demonstrate evolution in this process as well as for it to increase in number exponentially. A preliminary study has already shown that using RepRaps to print common products results in economic savings, which justifies the investment in a RepRap. History. RepRap was founded in 2005 by Dr. Adrian Boyer, a senior lecturer in mechanical engineering at the University of Bath in the United Kingdom. The first 4 official 3D printing machines RepRap project were Darwin, released in March 2007, Mendel, released in October 2009, Prusa Mendel, and Huxley, released in 2010. Although hundreds of variations exist, the core developers have named each after famous evolutionary biologists, as the point of RepRap is replication and evolution. However, other variants are often named after individual designers or names they prefer. The 23rd of March 2005, the RepRap blog is started. Summer 2005 funding for initial development at the University of Bath is obtained from the UK's Engineering and Physical Sciences Research Council. 13. September 2006, the RepRap 0.2 prototype successfully prints the first part of itself, which is subsequently used to replace an identical part originally created by a commercial 3D printer. The 9th of February 2008, RepRap 1.0 Darwin successfully makes at least one instance of over half its total rapid prototyped parts. The 14th of April 2008, possibly the first end-user item is made by a RepRap, a clamp to hold an iPod securely to the dashboard of a Ford Fiesta. The 29th of May 2008, within a few minutes of being assembled, the first completed child machine makes the first part for a grandchild at the University of Bath, UK. The 23rd of September 2008, it is reported that at least 100 copies have been produced in various countries. The exact number of RepRaps in circulation at that time is unknown. The 30th of November 2008, first documented in the wild replication occurs. Replication is completed by Wade Bortz, the first user outside of the developers team to produce a complete set for another person. The 20th of April 2009, announcement of first electronic circuit boards produced automatically with a RepRap, using an automated control system and a swappable head system capable of printing both plastic and conductive solder. Part is later integrated into the RepRap that made it. The 2nd of October 2009, a second-generation design, called Mendel, prints its first part. The Mendel's shape resembles a triangular prism rather than a cube. The 13th of October 2009, RepRap 2.0 Mendel is completed. The 27th of January 2010, the Foresight Institute announces the Kartik M. Gadda Humanitarian Innovation Prize for the design and construction of an improved RepRap. There are 2 prizes, one of $20,000 and another of $80,000. The administration of the prize is later transferred to Humanity Plus. The 31st of August 2010, the third-generation design, Huxley, is officially named. Development is based on a miniaturized version of the Mendel hardware with 30% of the original print volume. First half 2012 RepRap and RepStrap building and usage are widespread within the tech, gadget, and engineering communities. RepRaps or commercial derivatives have been featured in many mainstream media sources, and are on the permanent watch lists of such tech media as Wired and some influential engineering professionals' news media. Late summer, fall 2012 there has been much focus on smaller startup companies selling derivatives, kits, and assembled systems, and R&D results into new related processes for 3D printing at orders of magnitude lower prices than current industrial offers. In terms of RepRap research, the most notable result is perhaps the first successful Delta design, Rostock, which is maturing slowly and has an initial working solution for experimentation by self-sourcing builders of some experience. While the Rostock is still in an experimental stage with major revisions almost monthly, it is also near the state-of-the-art, and a radically different design. The latest iterations use open beams, wires instead of belts, and so forth, which also represents some of the latest trends in RepRaps. 2013 hobby-friendly machines have been made to allow hobbyists and small companies to produce their own filament for 3D printing, thus bringing down manufacturing costs and allowing for small-scale recycling and experimenting with different plastics and materials. 2016 In early January 2016, RepRap Pro announced on their website that they are to cease trading on the 15th of January 2016. The reason given was congestion of the market for low-cost 3D printers and the inability to expand in that market. We have decided to close RepRap Professional Limited. The company will cease trading on Friday the 15th of January 2016. We will service all support and warranty requests up to that date, and fulfill all our outstanding orders. The market for low-cost 3D printers is now so crowded and so competitive that a small specialist company like ours cannot expand. So, because we are not bankrupt and we do not have any debts to pay, we have chosen to stop now while we are ahead and to concentrate on other activities. Note that our closure does not affect RepRap Pro China Limited. That is a completely separate company and they will continue. We are an open source company. This means that all our designs, software, source code and documentation are freely available online on our website and on GitHub. All that information will continue to be available into the future. We would like to thank everyone who has supported us in the past, either as customers or as contributors who have improved our open source products, or both. The fact that, unusually for a former company, we will be able to leave megabytes of useful information available to everyone in perpetuity is due in part to the support from those people. www.reprappro.com, accessed the 6th of January 2016 hardware. As the project was designed by Adrian Boye to encourage evolution, many variations have been created. As an open-source project, designers are free to make modifications and substitutions, but they must reshare their improvements. However, RepRap 3D printers generally consist of a thermoplastic extruder mounted on a computer-controlled Cartesian XYZ platform. The platform is built from steel rods and stud and connected by printed plastic parts. All three axes are driven by stepper motors, in X and Y via a timing belt and in Z by a lead screw. At the heart of the RepRap is the thermoplastic extruder. Early extruders for the RepRap used a geared DC motor driving a screw pressed tightly against plastic filament feedstock, forcing it past a heated melting chamber and through a narrow extrusion nozzle. However, due to their large inertia, DC motors cannot quickly start or stop, and are therefore difficult to control with precision. Therefore, more recent extruders use stepper motors to drive the filament, pinching the filament between a splined or knurled shaft and a ball bearing. RepRap's electronics are based on the popular open-source Arduino platform, with additional boards for controlling stepper motors. This architecture allows expansion to additional extruders, each with their own extruder controller. Major revisions: the first publicly released RepRap, Darwin, has an XY gantry mounted above a moving Z-axis print bed. Darwin's Z-axis is constrained by a lead screw at each corner, all linked together by timing belts to turn in unison. Electronics are mounted on the steel supports of its cuboid exterior, and on a second platform at the base. In an effort to minimize the number of non-printed components, Darwin uses printed sliding contact bearings on all of its axes. It also rearranged the axes, so that the bed slides in the horizontal Y direction, while the extruder moves up and down and in the X direction. This makes Mendel less top-heavy and more compact than Darwin, while also removing the overconstraint of Darwin's 4 Z-axis lead screws. The build envelope for Mendel is 200 mm x 200 mm x 140 mm or 8 x 8 x 5.5. One of the more popular RepRap variants from 2013 and beyond is the Rostock Delta-style RepRap software. RepRap has been conceived as a complete replication system rather than simply a piece of hardware. To this end, the system includes computer-aided design in the form of a 3D modeling system and computer-aided manufacturing software and drivers that convert RepRap users' designs into a set of instructions to the RepRap hardware that turns them into physical objects. Initially, 2 different CAM toolchains had been developed for the RepRap. The first, simply titled RepRap Host, was written in Java by lead RepRap developer Adrian Boyer. The second, ScaneForge, was written independently by Enrique Perez. Both are complete systems for translating 3D computer models into G-code, the machine language that commands the printer. Later, other programs like CLIC3R, Prontoface, Cura, Repetier Host were created. The closed-source KeySlicer also seems popular. Virtually any CAD or 3D modeling program can be used with the RepRap, as long as it is capable of producing STL files. Content creators make use of any tools they are familiar with, whether they're commercial CAD programs, such as SolidWorks and Autodesk AutoCAD, Autodesk Inventor, Autodesk 120 3D Design, Tinkersad, or open-source 3D modeling programs like Blender, OpenSCAD, and FreeCAD. Replication materials. RepRaps print objects from ABS, polylactic acid, nylon, HDPE, TPE and similar thermoplastics. Polylactic acid has the engineering advantages of high stiffness, minimal warping, and an attractive translucent color. It is also biodegradable and plant-derived. The mechanical properties of RepRap printed PLA and ABS have been tested and have been shown to be equivalent to the tensile strengths of proprietary printers. Unlike in most commercial machines, RepRap users are encouraged to experiment with printing new materials and methods, and to publish their results. Methods for printing novel materials have been developed this way. In addition, several recycle bots have been designed and fabricated to convert waste plastic, such as shampoo containers and milk jugs, into inexpensive RepRap filament. There is some evidence that using this approach of distributed recycling is better for the environment and be useful for creating fair trade filament. In addition, 3D printing products themselves at the point of consumption by the consumer has also been shown to be better for the environment. The RepRap project has identified polyvinyl alcohol as a potentially suitable support material to complement its printing process. Although massive overhangs can be made with using thin layers of the primary printing media as support, which are mechanically removed afterwards. Printing electronics is a major goal of the RepRap project so that it can print its own circuit boards. Several methods have been proposed. Woods metal or fields metal, low melting point metal alloys to incorporate electrical circuits into the part as it is being formed. Silver, carbon-filled polymers, commonly used for repairs to circuit boards and are being contemplated for use for electrically conductive traces. Direct extrusion of solder. Conductive wires can be laid into a part from a spool during the printing process. Using a MIG welder as a print head, a RepRap delta bot stage can be used to print metals like steel. The RepRap concept can also be applied to a milling machine. Construction. Other 3D printer designs and parts constructed by other means may be used to bootstrap the RepRap process by building RepRap parts. Many such machines are based on RepRap designs and use RepRap electronics. These are generally known by the name RepStrap by the RepRap community. A RepStrap is any open hardware rapid prototyping machine that makes RepRap parts and is itself made by fabrication processes which aren't under the RepRap umbrella yet. Some RepStrap designs are similar to Darwin or Mendel, but they have been modified to be made from laser-cut sheets or milled parts. Others, such as the MakerBot, share some design elements with the RepRap, but with a completely reconfigured mechanical structure. Although the aim of the project is for RepRap to be able to autonomously construct many of its own mechanical components in the near future using fairly low-level resources. Several components such as sensors, stepper motors, or microcontrollers are currently non-replicable using the RepRap's 3D printing technology and therefore have to be produced independently of the RepRap self-replicating process. The goal is to asymptotically approach 100% replication over a series of evolutionary generations. As one example, from the onset of the project, the RepRap team has explored a variety of approaches to integrating electrically conductive media into the product. The future success of this initiative should open the door to the inclusion of connective wiring, printed circuit boards, and possibly even motors in RepRap products. Variations in the nature of the extruded, electrically conductive media could produce electrical components with different functions from pure conductive traces. Not unlike what was done in the sprayed circuit process of the 1940s named electronic circuit making equipment, described in the article on its designer, John Sargrove. Printed electronics is a related approach. Another non-replicable component is the threaded rods for the linear motions. A current research area is in using replicated Saris linkages to replace them. Project members. The core team of the project has included Dr. Adrian Boyer, former senior lecturer, Mechanical Engineering Department, University of Bath; Michael S. Hart, creator of Project Gutenberg, Illinois; Dr. Forrest Higgs, Process Innovations, Inc., California; Rhys Jones, postgraduate, Mechanical Engineering Department, University of Bath; James Lowe, undergraduate, Mechanical Engineering Department, University of Bath; Sebastian Baylard, Ontario; Simon McAuliffe, New Zealand; Vic Oliver, Diamond Age Solutions, Limited, New Zealand; Ed Sells, postgraduate, Mechanical Engineering Department, University of Bath; Zach Smith, United States; Eric de Bruijn, the Netherlands; Joseph Prusa, Czech Republic. Project sponsors include Rhys Arnott, the Bath University Innovative Manufacturing Research Center, the Engineering and Physical Sciences Research Council, the Fluorocarbon Co., Limited, Michael Ingram, Lukasz Kaiser, the Nuffield Foundation, Carl Whitty. Goals. The stated goal of the RepRap project is to produce a pure self-replicating device not for its own sake, but rather to put in the hands of individuals anywhere on the planet, for a minimal outlay of capital, a desktop manufacturing system that would enable the individual to manufacture many of the artifacts used in everyday life. From a theoretical viewpoint, the project is attempting to prove the hypothesis that rapid prototyping and direct writing technologies are sufficiently versatile to allow them to be used to make a von Neumann universal constructor. The self-replicating nature of RepRap could also facilitate its viral dissemination and may well facilitate a major paradigm shift in the design and manufacture of consumer products from one of factory production of patented products to one of personal production of unpatented products with open specifications. Opening up products' design and manufacturing capabilities to the individual should greatly reduce the cycle time for improvements to products and support a far larger diversity of niche products than the factory production run size can support. Education applications. RepRap technology has great potential in educational applications. RepRaps have already been used for an educational mobile robotics platform. Some authors have claimed that RepRaps offer an unprecedented revolution in STEM education. The evidence for such claims comes from both the low-cost ability for rapid prototyping in the classroom by students, but also the fabrication of low-cost, high-quality scientific equipment from open hardware designs forming open-source labs.